Okay.
Well, we're starting now, so I'll be back afterwards. That's okay, so let's get started again. So what we talked about is that QFT and quantum mechanics have exactly the same physics content. And in particular, we talked about this one. This comes for every the harmonic oscillator. This gives you the kinetic energy, and then we produce this chemical potential and interaction term. Which turns out to be completely the same thing as the quantum mechanics of interacting particles. And now I'm writing everything in 3 dimensions. So the only thing I did is to change dx to d cube x here. And correspondingly, now x derivative is now a vector, p is a vector, x is a vector, but that's the only difference. And so we set these to actually completely equivalent. But it turns out that if you're dealing with quantum mechanics, this looks simple enough with this delta function with also potential, but it turns out that you can't solve for the ground state. But in QFT side, you still can, as long as this parameter is small. Wait. Sorry, I misplaced it. Lambda squared mu m cubed h bar 6 is much smaller than 1, then can solve for the ground state in QFT. And the reason why this funny combination appears is because this combination is dimensionless. So when you think of some limit where you can solve the theory, and then ask the question, what will be the corrections to that limit? Let's say you're solving for ground state energy or something. Ground state energy or something. Then you have some zeroth order approximation, you have some correction, second order correction, third order correction, and stuff like this. And you hope that this is actually only small corrections so that you don't have to worry too much about it. And leading order is actually a good approximation to the system. And that happens when this expansion parameter is much smaller than 1, right? And in electromagnetism, you have seen this parameter alpha, namely fine structure constant. And as you know, this is 1 over 137, which is much smaller than 1. So indeed, when you do QFT calculations in electromagnetism, the leading order effect is something you can compute in classical electromagnetism. Then you have the correction, the second order correction, and so on and so forth. And because alpha is a small parameter, it turns out that just keeping the first one is already a pretty good approximation. Sometimes you want to look at second first order correction and so on and so forth. So the idea here is that when you're dealing with some quantum system, you can solve exactly, that's actually most of the cases. A case like a harmonic oscillator in hydrogen atom is actually an exception rather than norm. So most cases you can solve the system exactly. But you can do an approximate solution by identifying a small parameter and then deal with whatever physical quantities you'd like to compute in power series expansion in that small parameter. And because this is supposed to be correction to 1, clearly this has to be dimensionless. So one of the first job you do when you look at the system is by identifying parameters, you try to find a dimensionless combinations among them. And that would be out of the whole lot of problems, so you can actually do it yourself. But at least you need to see how that works. The parameter lambda is a part of Hamiltonian, so clearly it has the dimension of energy. But you have delta function. Now we're dealing with 3 dimensions. So that means this one has a dimension of length to a cube inverse. So lambda has the dimension of energy times volume. Mass, of course, is the mass. Mu is the chemical potential, has a dimension of energy. And you know what dimension of h bar is. It's energy times time. And you can make sure that everything is consistent by knowing that the Lagrangian, when you integrate over time, is an action. And action has a dimension of energy times time as well, which is the same dimension as h bar. So classical action somehow already knew that there is some important constant which has dimension of action. And I don't know why, again, somehow 19th century physicists were just amazingly ingenious, I guess. But anyway, so that's something you can do a cross-check by identifying each term in the Lagrangian. And in particular, you want to know that psi dag of psi has the mass dimension of length inverse cube, because this has the meaning of number density. We talked about that. So when you integrate over the entire space, that becomes the number operator. And this, of course, has the dimension of length cube. So this should have dimension of length inverse cube, so that the integral gives you a dimensionless constant, namely a number of the particles, which may be huge, 10 to the 23, but nonetheless is a dimensionless number. So that's the way all the dimensions would work out. And you're going to check that combination at the top of this blackboard is indeed dimensionless. So that's something you need to check. And just in case that why small number like that one would justify solving classical field equation. And I'm not going to fully explain this because that goes beyond the scope of the class. But the reason why Schrödinger could come up with the Schrödinger equation is by making this identification that the wave function is a wave given by the classical action. And assuming h bar is a small parameter, this wave would oscillate very quickly. Which means that only the stationary solution would contribute. So if you think of S to be some complicated function, and because of this small h bar, this oscillates very quickly, but when S is somewhat stationary, then this area doesn't oscillate too quickly. So that will be the important contribution. And the stationary action is what gives you the Newtonian equation of motion as the Lagrange equation. So that's the way he actually came up with the Schrödinger equation. He could guess Schrödinger equation because of identification, and he made sure the Schrödinger equation would reproduce classical equation by looking at this classical action in the exponent. So that's how he actually came up with this idea. Then it turns out that in our case, we have this action in QFT. And if you play tricks, like changing the normalization of the field operator psi, changing the unit for space and time, you can cast this. Maybe I can erase this now. Into the form that looks so this is time in different unit, space in different unit. This is also psi after changing its normalization. So that you can remove dependencies of the parameters completely out of this action, except that they all appear in this prefactor. And with this combination is large, or otherwise this inverse, which is the one up there, is small. Going back to the original argument by Schrödinger, this is the action which appears in the exponent. And if that parameter is small, that is the same thing as h bar being small, so wave function would oscillate very quickly. Then your solution is dominated by the stationary solution of the action, which is nothing but the classical equation of motion. And I've not explained this fully because I haven't had time to explain why this identification makes sense. But if you have seen the idea of the path integral in quantum mechanics class, and have you seen that? Some of you did, not everybody. But in that case, you really put in this e to the is over h bar and integrate over all possible trajectories of particles. And once again, if h bar is small, this thing is supposed to be inside this gigantic integral, but the stationary point would contribute the most because this oscillates so quickly. So that's the way you can justify this argument. So it turns out that when this parameter, inverse of this parameter, is small, then the solving classical equation motion is justified. And that is what is called the semi-classical technique.
I have a question.
Yeah, I get to that.
If you take the classical limit, which is the time constant to 0, then it seems like the dimensionless parameter will be infinite and not 0. That is not consistent with our intuition that.
Yeah, so that's a good question. And I have to emphasize that we are not taking a classical limit in any way. H bar is still there. And just like in the case of the coherent state we talked about in harmonic oscillator, we have this minimum uncertainty state in x and t. So h bar is still there. I'm not taking a limit of this going to a point. But this is small enough that we can pretend that this solution is sort of similar to the classical motion of the harmonic oscillator pendulum, but uncertainty is still there. And that's why this is always called semi-classical. We are never taking the classical limit. But it turns out that solving for the ground state, when certain combination is small, turns out to be the same thing as solving classical equation of motion, even though this is still quantum theory. And this is the way we can actually get, for example, the Wi-Fi signal. We are going to write down the operator as an action for the electromagnetic field later on. But the reason why we can just go ahead and solve the Maxwell's equation to find the classical radio wave is because, again, wave function oscillates so quickly, and we can actually pretend that solving the classical equation of motion is the right thing to do, even though you are dealing with a quantum system. And that's why this is called semi-classical treatment, not classical treatment. Okay, that's a very good question. Any other questions at this stage? Is it okay? All right, so then we start to actually solve this classical equation. And classical equation motion is IH1 psi dot. And we found very boring solution when mu is negative. But it is a solution nonetheless, because psi equals 0 in terms of an operator corresponds to this requirement on the ground state, which said this is the vacuum state. So when mu is negative, it costs you energy to put in more particles. So you are better off not to have any particles at all to minimize the energy. At the end of the day, you find this boring but simple solution, so at least it does make sense. But when mu is positive, we found the solution is actually non-trivial, because even when this is static, just a constant, doesn't depend on x and t, if you substitute this into that equation, you find this equation, you can factor psi out. That gives you a non-trivial solution. Psi sub psi is mu over lambda, which is now positive. And then you also find that there are actually infinite number of solutions to this. Psi is square root of mu over lambda times arbitrary phase. This is undetermined. And the idea was that solving this equation is supposed to give you information on the ground state. It turns out that there are actually infinite number of ground states. And that sounds crazy. When you solve for the ground state of a hydrogen atom, the oneness state was the ground state. That's it. In harmonic oscillator, the lowest energy state was unique. There was no infinite number of ground states. But it turns out that there is indeed an infinite number of ground states in this case, which actually turns out to be very important later on. For now, we don't get too much into it. Just go ahead and think about the solutions to this equation. But we will come back and talk about why that's an important thing later on. And to understand the solution, I draw this picture. That negative mu psi sub psi plus lambda over 2 psi sub psi psi psi. And you can view this as a potential as a function of the field. That's a new concept. We haven't discussed this before. So when you talk about a potential as a function of space, you know what that is. You have some, say, electric field or something. And if you place a particle in electric field, it gets pulled by the electric field in one direction, and that's proportional to the gradient of the potential. That's something you know very well. Now we are talking about the potential as a function of the field, because the Lagrangian is supposed to be kinetic energy minus potential energy. So the pieces down here, up there, sorry, the last two terms is negative of the potential, but for the field. And when you solve for the equation of motion, then static solution is always at the bottom of this potential. So if you actually plot this, this is the real part of psi, here's the imaginary part of psi, and it depends only on the phase, so it's actually axially symmetric like this. I hope this makes sense. So if you draw this shape from negative quadratic terms, it goes down, and positive quadratic terms, so you will eventually take it over, and then potential starts to go up. And if you plot this on this complex plane of the real part of psi, imaginary part of psi, depends only on the modulus of psi. So it's actually sort of axially symmetric. So you plot this and then rotate it around, and I hope this looks sort of three-dimensional enough so you can get what's going on. then clearly the bottom minimum of this potential is along this trough. That's where psi sub psi has a value of mu over lambda. But anywhere along this trough has the same energy. And that's why there are infinite number of solutions along this trough for whatever phase you pick for the solution of the field. So that's what we talked about. And I also told you that solving this classical field equation actually turns out to be looking at the field operator, giving you the eigenvalue. So that's the coherent state. And what we have just done is the same thing as taking the variational method so that you evaluate expectation value of Hamiltonian between these coherent states, and then you minimize it. To find the solution. But when you evaluate this expectation value, conveniently, psi is always on the right in that expression. So they act on this coherent state directly and pick up its eigenvalue. So all it does to insert this function f into psi of x. And same here, when psi dagger acts on this coherent state draw, and that picks up the complex conjugate of the eigenvalue f. So you just insert f star in there. And then the stationary condition is the same thing as solving this equation of motion. So it turns out that what we are doing is actually variational method. So variational method, which you learned in quantum mechanics class, using coherent state as an ansatz for the ground state wave function, turns out to be completely equivalent to solving classical field equation, which I told you turns out to be the right thing to do in a limit where this dimensionless combination of parameters is small. So that's what we did. So instead of trying to solve the problem of the quantum mechanics of these interacting atoms and large number of them together, it turns out that going to QFT and just simply solving for classical field equation is actually meant to be exact solution to this interacting quantum system as long as that combination of parameters is small. And that combination of parameters actually turns out to be very simple condition that when you have this bunch of atoms in your system, and of course they interact because of the potential, but in the limit where that combination is small, mean free path of the particle, so kind of typical distance for the atom to hit another one, is much greater than inter-atom separation, which is fixed by the density of the gas, right? Once you have a density, the typical separation between them is the cube root inverse of the density. And if that inter-atom separation is much smaller than mean free path, this is sort of close to free particles, even though they do interact. That's when this approximation becomes justified. So what we are talking about is actually a very dilute gas of atoms. So in that situation, this approximation is valid. Therefore, this solution is supposed to be valid. Then you find this weird situation where a field operator has a value, namely it's a coherent state. And as you know already, coherent state is actually a linear superposition of states with different number of particles in the system, which you can talk about in QFT, but you can never do in quantum mechanics, because in quantum mechanics, Hilbert space has a fixed number of particles in it. You can never even talk about how you take linear superposition of states with different number of particles, because you're talking about wave functions with different number of arguments. But in QFT you can, and that was actually needed in order to solve for this ground state of the system. So that's the first time you actually see the power of QFT. You can do something which you couldn't in quantum mechanics. Okay, so this is a good time to point to stop. Any questions? Yes?
Could you explain again why V is a function of the field operator?
Can you say that again?
Could you explain why V is a function of the field operator and not just space?
D?
The potential.
Or V?
Yeah.
So this V, oops, is it stuck? Oh no. It's just this piece. So Lagrange is kinetic energy minus potential energy. And this piece doesn't have any derivatives in it. So that's why this piece is called the potential.
Yeah, but I mean, why wouldn't it not be like just a function of space? And why does it have to be a function of
So
space?
it can include space. Because in principle, field
Yeah.
is a function of space. But we have this intuition that looking for the ground state of the system is probably something very homogeneous. Then there is no sort of variation with respect to space. And when we look at excited states, we will actually talk about psi dependent on X. But if you're only looking for the ground state, then this is the homogeneous case. That's why I dropped X dependencies from this potential. And that's why I could just draw it. But in principle, this potential is there for every position in space.
Okay.
Okay?
Yeah.
Thank you for that question. Anything else? Yes?
Could you clarify what classical field equation is again?
Say that
Could
again?
you clarify what classical field equation is and how it's different from quantum?
So this classical field equation was derived from that classical Lagrange just by taking the variation of the action with respect to psi star. So when you take variation with respect to psi star, this is varied, multiplied by this. This is varied, multiplied by the rest. I do the integration by parts. This is varied, multiplied by that. This is varied for this factor of 2, so that cancels factor by half, multiplied by psi star, psi psi. And so that should vanish to make sure that the action is stationary. And that's the way you get this equation. And we are solving this as if psi is just a function of space and time. And of course, we assume that it's actually simply a constant, so not even a function, it's just a number. But what I argued today is that solving this equation turns out to be solving for the ground state of the quantum system. We can treat it as if this was the classical equation of motion, but in principle, we are still solving for the quantum ground state. That's why this is called semi-classical instead of classical. Does that answer your question? Not quite.
Yeah, I still don't really understand what it means by classical compared to quantum.
What I mean by classical here is that psi is actually an operator, right?
Yeah.
So this is in principle an equation among the operators. But I'm solving this equation just by this. And here, psi sub psi turns into just numbers. So that's what I meant by solving classical equation. So I'm treating psi as if it is just a function of x and t, not as an operators. So that's what I meant by saying that I'm solving classical field equation. Okay? Anything else? Over there.
So previously when we talked about potentials, you mentioned that they're always scalars, but in this case the potential is a function of size, so it seems like it would be an operator.
Yeah, so it is in principle an operator. So this potential, of course, is an operator too. So psi is an annihilation operator and psi dagger is a creation operator.
Okay.
But because we reduced the problem to solving the classical field equation in the end, even though we are still thinking about solving quantum system, then I'm treating psi as if it were just a regular functions instead of an operator. And then we can just look for the minimum of this function. And that gives you this idea that a ground state is actually a coherent state in the A.
So it's an effect of taking this.
Yes, that's a technique. Yes. Yes.
So, right when we try to rewrite the field operator psi as a complex operator, well, we do have the expression of square root of mu over lambda.
This one.
Yeah, and this one actually corresponds to why it is a axisymmetric. It is axisymmetric graph.
Yeah, because the solution has to satisfy this psi stop psi to be constant. Yeah.
Yes. So because we now have the because we want to carry out perturbation, which is why we want the lambda square mu m over h bar to the power of 6 to be really, really small. And if we want it to be really, really small, then it means that lambda and mu must be also small.
Lambda
Then-
and mu must be small. Where did it go? I erased it?
It's right there.
Well, as long as this combination is small, that's okay.
Because, so if we were to actually look at the position of psi in the graph, then I want to know, like, for psi with, say, small mu and huge lambda, then it's dominated in the low area, or
What do you mean, low area?
low region, I'd say. Smaller radius, right? If I have a large.
What do you mean, the radius of this
Yeah.
potential?
Because I wanted to know, like, in a bigger picture, like, I can always zoom out and I can see like parabola shape.
Okay.
Then it is only significant when it's like when the radius is small, so that we consider a shape like this.
I'm not sure what you mean. So the one point here is that the psi leg of psi has the meaning of the number density, right?
Yeah,
So it has actually some dimension.
yeah.
So when you say the number density is small compared to something, you have to know what you compare that to.
Okay.
So there's no, it's not actually a well-defined question. If you're comparing with some other systems which you know and understand, that may make sense. But right now we are only talking about this system, we're not comparing to anything else. So there's no way to say this is small or large, it's all relative, right? So that's not a well-defined question, it turns out.
Yeah, yeah.
Only when you look at some dimensionless combination, then you can definitely compare that dimensionless number to 1 to see if that is small or large on some absolute scale.
Then I do have a question.
Yes.
Then, say if now the whole factor is say equal to 1.
Whole
then,
factor?
The whole factor, like a lambda squared.
This one, yeah.
Yeah. If the whole factor is say equal to 1, then the graph should look like this.
Well, so
Or
in
it
that
should
case, I
be
don't
like
even
this.
know how to draw a graph. Because solving for this field equation
Yeah.
is not a good approximation in that case. If you start thinking about corrections on top of the solution you get, then the corrections are supposed to be order 1. So you're making 100% error. Then you don't really know what you're talking about.
Oh.
So the thing is that, again, because in most systems in physics you cannot solve exactly, you have to always resort to some kind of approximation. And when you're looking at the dilute gas, It just so happens that this combination is small, so that you can trust what we are doing right here. And when you are in the other limit, maybe you can find different way of solving the system approximately. But this technique certainly would not work in this case.
Understood. Thank you.
Yes?
Does the phase matter of the design?
Yeah, so in the end it does matter, and we'll come back and talk about that.
Because solving that equation essentially means the wave doesn't oscillate at all, right? Because it's a constant.
As a solution, yes.
Yeah, the solution is a constant.
Right.
So it means the wave function is like a line.
Yeah, but I think you asked the question, what about the spatial dependence? So in the end, we have to think about this potential being attached to every participant in space. And then you can think about, maybe your field is here at this position, but changing slightly to another one, and change slightly to yet another one over here, then you're looking at now, it really looks like a wave. It changes from one position to another. But that wave costs you very little energy because you're always staying at the bottom of the potential.
Oh,
So that turns out to be actually what we call the phonon. That's the quantum of sound. And that actually costs you very little energy. And we'll come back and talk about this. But it turns out that this phonon has a spectrum as a function of its momentum, that it really starts out with 0. So for very long wavelength change of this phase, a long wavelength corresponds to small momentum, right, to Broy's relation. So you are somewhere here. And because you never climb on the potential hill, that costs you very little energy, so energy is tiny. And it turns out that this is actually linear, where c is speed of sound in this case. And this actually turns out to be the important point to know that this collection of atoms in this cold gas turns out to be actually have 0 viscosity. It becomes a superfluid. It can flow forever. And so that's the thing that we will discuss later on, and that actually has to do with this fact that energy goes to really 0 linearly as a function of momentum, and that corresponds to this slightly spatially varying ground state.
So can I understand it as if I keep this ball and moving it through space, then the point at the bottom is like going this way?
Yeah, so we will actually talk
Then
about that
what
solution.
pushes the phase?
So let's look at the solution, and I hope that will actually give you a better idea.
Yeah.
Yes?
You might justify that you're treating sine by dagger as a function instead of an operator.
So when we solve this equation, we are regarding this type to be just a function of space and time, not operator.
Yeah, why is that justified?
So that's not justified because of this idea that solving for dominant contribution to the wave function is given by the stationary condition of the action. And that's also the same thing as saying that we are using this coherent state as an ansatz to the ground state. And when the field operator acts on the coherent state, it just pulls out the eigenvalue. So the operator turns into a number. And then we are minimizing energy with respect to this number f. That's the equation itself. Okay? Anything else? Okay, so this is the static solution. So let's look at something a little bit more interesting. So we have this solution, we have this equation. Sorry. And then you find that there is actually a solution which is a little bit more interesting, which is that this now depends on both space and time. And one thing you notice here is that even though up to this point, this may look like a Schrödinger equation, but it definitely isn't, because Schrödinger equation has to be linear. Otherwise, this whole idea of quantum superposition wouldn't work. But this equation is non-linear. If you find a solution, and if you make the solution twice as big, it's no longer a solution because this is non-linear. Normalization matters. So this is a non-linear field equation. Which is definitely not Schrödinger equation. And there is a way of calling quantum field theory as the second quantization. You sometimes see this name in the literature, and I would say that's a totally wrong name. But the idea came from this fact that if you have a particle, you quantize it, then you have a wave function that follows the Schrödinger equation like this one. Then you say, okay, we got this psi thing, and whatever that is, we are now doing the quantization again to make psi an operator, and hence second quantization. And that's a sort of historical name for QFT. But I would say that's a totally wrong name, because now psi has a meaning of the creationization operators, and you have seen that what follows the Schrödinger equation as a wave function was the coefficient of the creation operator you acted on the vacuum state. That's how we made sure that quantum mechanics and QFT were the same thing. So they have totally different meanings. So call this second quantization is a wrong name. But you might see that name in the literature, so at least you need to know it. And whenever you see second quantization in a paper or textbook, you just speak to yourself, this is a wrong name, okay? So it's a wrong name. And that's why you call this quantum field theory instead. And the interesting thing about quantum field theory is that we are dealing with this kind of non-linear field equation, which of course makes it mathematically a little bit more complicated, but in this case, at least you can find solutions like this one. And the reason I'm emphasizing it is that this normalization factor is not something I can change. And this normalization factor is the same as the normalization factor I had over here, which has the meaning of the number density. So here we're looking at the solution of fixed number density, and the entire gas or fluid just stationary. But now we are looking at a solution which depends on position in space. So clearly something is moving now. And to make sure that this is indeed a solution is actually very simple. We just plug them in here. Here's a time derivative that would extract IH bar. And here's a time derivative, which comes down from the exponent. Here I have a spatial derivative that is x, that pulls out I over h bar mv. And you can check that these two completely cancel against each other. So the first two terms in this equation cancel against each other. And third and fourth term, you can also see they cancel against each other, because this spatial and time dependence is just a phase factor. When you take absolute squared, this cancels. So psi sub psi is still mu over lambda, just like the original stationary solution. So mu and lambda psi sub psi cancels. So the third and fourth term cancel against each other. So that's how you can see that this is the solution to this non-linear field equation. But now you see this dependence on x and t. And as you know, when you have a phase factor like this one, you can identify wave vector and frequency. And as you must have seen somewhere, the group velocity of a wave is given by k derivative of omega. Here, omega is given by this one. K is given by this one, both of them over h bar. And if we just go ahead and compute this, this turns out to be D itself. So the solution we are looking at is a solution which corresponds to this entire gas moving with a constant speed. So now we are talking about some kind of fluid, but we still can't know what exactly that is. Until we start looking into some experiments. And people use often some alkaline elements like lithium, cesium, sodium, and so on, just because they are easier to control. And what they do is to have some oven with a gas, with a hole, and you take the atoms out, and you trap them in some kind of potential. One of the things people try, for example, is that when you have a magnetic field applied, which you can choose to vary in space, and energy can contain this coupling of the magnetic field to magnetic dipole moment. And for alkaline elements, you have one electron as a valence electron in outermost orbit. It's not paired. So one electron, of course, has its magnetic moment. So magnetic moment doesn't vanish. And when magnetic moments are aligned in the direction of the magnetic field, you lower energy. So if this is actually a profile of the magnetic field, then the electron whose spin is aligned with the magnetic field has low energy, which now depends on space, which means you can accumulate the atoms this way inside this trap. So this is called magnetic trap. And then you start to cool it. And if you have watched the video I asked you to watch last night, then last technique is called evaporative cooling. And in that video, the guy's explaining that it's like sort of blowing a cup of coffee. And the idea is that when you blow a cup of coffee, the molecules in coffee have some distribution. Some of them is moving fast, some of them is moving slow. And if you blow it, the molecule that's moving fast tends to sort of leave the cup very easily. Then those with slow speed tend to stay. So basically you are letting the fast moving ones out of the system, and you keep only the slow moving ones. And if you have only the slow moving molecules in the system, that means it's cold. So that's the way you can cool the system, and eventually all the way down to nanokelvin, which is incredible. But when the temperature goes down to nanokelvin level, then the wave functions start to overlap for individual atoms. And that's something you have also seen in the other video I hope you have watched earlier. So what do you know is Equipotential Theorem. You learned this in freshman physics class? So every degree of freedom when you look at the Sobo average, it's given by half kT. That's the equipotential theorem, right? So if you add them up, this will be half kT. So that gives you the average momentum to be 2m over here 3mkt square root. Then just from this one, you can estimate how big the wave function of the particle is, because P tells you how much momentum is spread, how much wave function spread is delta x. This has to be bigger than h bar or so. So the size of the wave function then is at least bigger than inverse of this. Then you ask the question whether this becomes bigger than inter-atom spacing. And that's the video you watched before the Wednesday's class, that when temperature becomes low, denominator becomes small, so delta x becomes big. So what used to be sort of individual atoms like this one, they start to spread. They start to overlap, and that's when the different particles can overlap with each other. Then you start to talk about basically linear superposition of maybe 1 and 2 particles here and so on. Eventually the whole thing becomes a big blob. And that's where you have this Bose-Einstein condensate. And what experiments have shown is something like this. And I hope you will look at the slides later on. Can I pass this around? Because it's in color. My printer is only black and white, so I'm sorry about that. So what's showing there is how things look like when you cool the system in momentum space. And this is something you can measure. Basically, you put the system into a trap, and if you actually remove the trap, atoms start to move out, and you can measure its momentum, and that tells you how momenta are distributed. And initially, it's sort of spread out all over the place, but then as you cool the system, it starts to accumulate here with a high peak, which means all the particles start to come to the zero momentum states. And that's not allowed for fermions, because the two fermions cannot occupy the same zero momentum state. But for bosons, they can. So eventually, all the atoms end up being in this zero momentum state. And that's what we call the Bose-Einstein condensate. And I realize not everyone has taken the StatMech class yet, but when you go to StatMech class, something called Bose-Einstein distribution comes with a sum of one particle with a kinetic energy P squared over 2m. But then you add the chemical potential. And in this case, one particle is just mu. If you have two particles, you have twice this, and also twice this, and you sum them up. Then they sum up into a geometric series. And I've got beta here, sorry. Beta is 180. And if this particle is completely free, this is supposed to be good enough. But then you notice something strange, because when momentum is small, then p square of 2m minus mu can vanish in momentum space. And that becomes a circle. Inside that circle, this thing becomes less than 0. So this actually becomes negative. Probability turns into negative. Exactly when these two are the same, then this becomes 1 minus 1, probability becomes infinite. So something is wrong. And what is wrong is that you ignore interaction. So if this is a free particle, this is good, but it's not. It can't be, because the probability becomes divergent and negative, and that's really crazy. So that's why this is a signal that the macroscopic number of particles start to occupy these very low momentum states. And that's exactly what you have seen in this handout, that you see this big peak of density for very low momentum region, and hence Bose-Einstein condensate. So the idea is that when you have a system of cold atoms, and you start cooling, eventually all the atoms start to want to go down to the lowest energy state, namely low momentum states. So macroscopic number of atoms start to occupy the same quantum state. And this is actually a very unusual, highly quantum state of matter. And once you have that, and you can create two of those, and the idea is that you create two of these things in potential trap. Another one get over here. And you cool them down, so both of them becomes these Bose-Einstein condensate. And then you turn the knob and shut off the magnetic field. Then they are no longer trapped. They start to fall while also expanding. So as this expands while falling, as this also expands while it's falling, they start to overlap. And that's where you start to seeing these fringe patterns. And as I said the last time, this fringe pattern is not like double slit experiment, where you can see the fringes only after repeating the same experiment over and over again. That's the fringe pattern for the probability wave, because each time you can predict where you're going to find your electron. This is different. You have macroscopic number of atoms. When you shine light on it, you see a different amount of absorption of light, which translates to the density of atoms. So you can clearly see how the density of the atoms distributed on one shot, just by shining light on it. And with a single experiment, you see this fringe pattern, which means that this is the interference of some kind of macroscopic wave. So this is what I was trying to do here, namely that by considering a system of atoms with this weak repulsive interactions among each other, and at cold temperature, this classical wave ends up describing this highly quantum state of matter. Maybe it was here. No, I erased it. So that when you see two waves, like what I brought down before, psi 1 is combination of these parameters, e to the minus I over h bar mv1x, and psi 2 mv2x. And when they start to overlap, you add them and take absolute square which is the density of atoms you observe by shining light on it. Each term absolute squared just gives you constant, which is the number density of each blocks. But there is a cross term proportional to the geometric mean of the number densities, and then you multiply them with the minus sign here, add the complex conjugate, so this one becomes twice the cosine, and then what you find is that mv1 minus v2x minus half v1 squared minus v2 squared b. And this x dependence in space, in cosine, means you have a fringe. So what you saw in this picture is something really remarkable, namely that by just cooling the system of gas, they start to behave like a classical wave, start to interfere and show fringes. And this is a highly quantum state of matter. But it turns out that the way you can understand this highly quantum state of matter is by simply writing down the classical field equation. And that's the particle wave duality. So if you start with particles behaving like a wave as a collection of particles is a highly quantum state. On the other hand, in QFT, you start with a wave and you get particles after quantizing it. But it turns out that the coherent state of QFT is actually a classical wave instead of classical particle, and that actually gives you the right description for this Bose-Einstein condensate. So if you happen to grow up in a world at the nanokelvin temperature, this will be your daily experience, and you wouldn't think of this as made of particles. You'll probably develop your physical theory based on everything is being wave instead. But by raising the temperature, at some point you might discover, oh, these things are actually made of particles. Where did they come from? Then you start thinking about quantizing that wave and come up with the creation-addition operators to describe particles out of a wave. But we happen to grow up in a much higher temperatures. What we typically see is the atoms zooming around in this molecule. You don't see them, but anyway, we know that. So they behave like particles. So that's what we normally think of the starting point of theory. But when you go down to lower temperatures, each particle starts to become bigger in size of the wave function. That's when you say, oh, what's going on? Then start to think about quantizing particle and then talk about waves instead. So it's just the opposite way of approaching the same problem, it turns out. And that's the particle wave duality. But for this purpose, starting with a wave is definitely a lot better description. Because if we want to use the particle language to describe this state of matter, that would be probably very, very complicated. I don't know how to do it. And you can't certainly take a linear combination of them to form a coherent state. So the QFT is must once you start talking about stuff like this. And you'll be raising your hand, sorry.
Yeah. Yeah, so we described the Bose-Einstein condensate by taking superposition of states. But the equation in QFT that we found is non-linear, so how
That's right.
are we allowed
So
to
this is not a solution. So you take this as the initial condition for the wave equation, and then you solve what happens next, then it wouldn't look like this anymore at some point.
Yeah, but the states that we're describing are QFT solutions to the nonlinear equation, right?
Right.
So how are they allowed to superimpose and still obey the equation because it's
So it's not a solution to the equation of motion. So maybe I shouldn't put T dependence here. So this is sort of the initial condition when they start to overlap with each other. So as long as each block is separate, then they follow these individual solutions. And when they start to overlap, then you sum them, but it's not solution to the equation. This is just the initial condition for solving the field equation. And then it starts not looking like this for the rest of the time evolution.
Yeah, but what about before two condensates are superimposing each other? What about the formation of the condensate itself?
Formation of the condensate. So this is the equation for the condensate already. So condensate has been already formed and described by this solution. Am I answering your question?
Yeah, I was just confused, like, when we are saying that the Bose-Einstein condensate is formed, that's formed by superposition of the wave functions.
Oh, for particles, yeah.
Yeah, for the particles. But how are we allowing the wave functions to superpose?
So what I'm saying is that once you go down to very low temperature, they get all spread out, and then this whole system is then described by this solution.
I see, okay.
So before the condensate forms, this actually doesn't make sense.
Yeah, okay.
So only after macroscopic number of particles that occupy the same quantum state, collectively, they start to follow this wave-like behavior. And only after forming these two condensates separately, I just make them overlap. And the minute they overlap, they start to look like this. But the rest of the evolution, you have to solve probably numerically how the rest of the evolution goes.
So that function here is not describing the actual wave function of the actual particles.
No, no.
So it's just the shape of the wave function.
That's right. That's right. So because the square of this is the number density, not the probability of finding a particle at a given position. Yes?
At what point did we assume that where low temperature should derive the classical wave equation?
So far, I basically didn't put temperature anywhere here, right? So I'm assuming it's zero temperature. If it's the finite temperature, then I have to start thinking about excited states too. And as you probably have seen in freshman physics, once you have excited states at finite temperature, they are distributed according to Boltzmann weight, and I have to consider the collection of them. So to do so, at least I have to talk about the excited states on top of this ground state I talked about, and that's the next subject. Yes?
So how are we able to use those solutions? Because those solutions were found when the mean free path was much greater.
Right.
But now that the temperatures are low, the mean free path must be small. And so how are we still able to?
No, mean free path is large. So even though you have all the particles overlapping with each other, mean free path means how long you travel before hitting another one. Being close to each other means inter-atom spacing is small, but mean free path of hitting another one is a different idea because that relies on the interaction. So mean free path is not the inter-atom separation, which is fixed by the number density, but rather how far you have to go so that you get disturbed by some other atoms.
But since they're close to each other, that should be small, right?
So if interaction is weak, then probability of hitting another one is small.
Yeah.
So that's why it can go long way before hitting it.
Oh, so but if the potential is high, we could not do this calculation?
Right.
Okay.
And so that's another interesting thing. So if you actually have this repulsive potential, you have this number density given by the chemical potential over this interaction strength, which kind of makes sense. So because there's a finite interaction, if you try to squeeze the gas, there is the resistance for doing so, because the particles start to hit each other and you feel pressure. So the stronger the interaction, then you end up with more dilute gas. On the other hand, chemical potential is an incentive of keeping a particle in a system. So the bigger the chemical potential, you tend to accumulate more particles. So this expression makes sense. And then what I was trying to say beyond that. And once you have number density, so the mean free path is usually defined by the inverse of the cross section for particles interact with each other times the number density. And cross section, do you study cross section in 137 scattering theory? Yeah. You know it, some don't. So the cross section is an idea. It's sort of like again, if it were classical mechanics, suppose you are very, very bad at dot, and you throw them randomly, and target is small, so you have a very small probability of hitting it. So basically, the bigger the size of the target, you have more chance of hitting it. So this cross section tells you how often you can hit it, hence the idea of the cross section. But if you have a certain number density of these targets, even if each cross section is small, you would eventually hit one. And the denser this collection, closer you're going to hit it, and that's why you multiply these numbers together, and inverse of that tells you the mean free path. So interparticle spacing is not the mean free path, because it really depends on this cross-section, which tells you how strong the interaction is. So this is proportional to lambda, and actually worked it out actually somewhere. So it turns out that for this delta function potential, the cross-section turns out to be lambda n 2 pi h bar squared. So the stronger lambda is, then cross-section becomes bigger. So small lambda means cross-section is small, so that even you have the collection of targets, you tend to go pretty far before hitting that one. So that's the idea of the mean free path. Does that make sense? Yeah. Okay, good. Yes?
Yeah, I have confusion. So you talked about how psi 1 and psi 2 can be written as e to the power of I sort of kx minus omega t.
Mhm.
This is only because it is now we're considering a collective, which is a high particle system.
Right.
And so collecting now means more like multi-particle system, or that the separation is must be lower than threshold.
Yeah, so this psi I've written and erased again is supposed to describe this entire system, because it's supposed to be the eigenvalue of the annihilation operator, which is the coherent state. So this is an operator. This is the ground state. Turns out to be this. And because it's a coherent state, it's an infinite linear superposition of states with different number of particles in it. And when f is large, which corresponds to this mu of lambda being large, then you, if you remember the quantum oscillator, you are very far away from the origin, which means that this uncertainty starts looking more and more negligible. And in the limit this is infinitely far away, then you can really treat it as if it were a classical pendulum. So that's when this classical treatment becomes justified.
So, so the psi 1 and psi 2 is just a description of a collective particle system with respect to, say, a position at that point.
That's right.
Understood. Thank you.
And then, now that we also have looked at this solution that flows, next thing we would like to talk about is flowing. So you put the system into this donut-shaped tube and let this gas flow inside. Then I will give you an argument that this should be a persistent flow. Which is meant to be that this is supposed to keep going forever. And of course, nothing is forever. So there's some limit to it. But there's a very, very little disturbances to the flow. And I will show that. And that means this is actually a superfluid. Because if there's any friction in the system, then you would expect that flow starts to decay exponentially. And that doesn't happen. So it's not really infinite, but it turns out that it starts to flow constantly, which means that there's no viscosity to disturb the system, and then boom, it disappears. And I'll tell you why, but anyway, so that this fact that there doesn't seem to be any disturbances to let the flow decay is a sign of this system being superfluid, namely it's a fluid with zero viscosity. And that's something you may have heard about. Do you do this experiment in 111 lab? The liquid helium superfluid? No?
Yes.
We do?
111B, yeah.
Ah, okay. Maybe in the pandemic that may not be happening, I don't know. But anyway, so there is actually something you can really do with your hands, namely cooling the gas of helium and make it into liquid. Then if you actually look at the liquid helium, it flows without resistivity. It can even do something really unthinkable. So again, if I had the slides, I could have actually shown the movie of it, and then hopefully I can put the link of the movie from the syllabus that you can watch it later. Suppose you have a beaker with a bunch of tiny holes at the bottom, and you fill this with the liquid helium. Then at higher temperature, it stays inside, stays in the beaker. But as you cool the entire system, at some point, it starts to actually cool down. For a while, it becomes bubbly. So that's the opposite from boiling water. So you go from high temperature to low temperature. So it starts being bubbly. Eventually, everything seems to calm down and it becomes a superfluid. And then helium starts to leaking through these tiny holes because there's no viscosity. So that's something you can see in experiments. Also, if you put it into sort of shallow vessel like this one, then you would think that stays in there, but it starts to climb up the wall and then starts dripping like this. Again, because of no viscosity, it can just keep going down without any resistance, and it finds its way to go down in potential energy by leaving the vessel, and it actually does that. It's a really crazy system. But that's what I meant by superfluid. Once you have a fluid with zero viscosity, it starts doing all kinds of weird things. But that does happen. And so the thing I want to show next is that you can understand why that is once you actually solve the equation in this the donut-shaped object. And being a physicist, I always think about the simplest setup. By assuming that this tube is infinitely thin. That's of course an approximation, but it can be a good approximation for a given system. Then I can come up with a simple solution to the equation of motion below down. Which is this. So I use the variable theta because I'm not interested in direction, radial direction at all. I'm just looking at this theta direction. Then I can solve that equation of motion as a function of theta. Like this. And again, you can see that the form of the solution is pretty much similar to what we had before, when everything is moving in one direction. Except that now I have this e to the I n theta instead of e to the I mv x over h bar. Now, main difference here is that in order for this field to make sense on a donut-shaped tube, n has to be integer. Otherwise, it's not a good function of theta. Theta would come back into pi. It needs to be a function of theta. If n were not integer, when you come back, you don't come back to the same phase. So that's ill-defined. So being this integer means that when you have a flow of this fluid inside this donut-shaped object, it can flow with this basically velocity given by n. So the flux of the flow starts out with maybe n equals 3 or something. Then it can change because there's no way to write a solution where n is 2.9 or 2.1. It can't continuously go down to 2. It has to stay at 3. The only way 3 can go down to 2 is a jump, which may happen, and that would correspond to tunneling process, because there's no solution in between, but you all of a sudden jump from 3 to 2. What's more likely to happen is that as the fluid keeps flowing like this one, even though it's meant to be dilute gas with weak interaction, sometimes a bunch of atoms might actually come together accidentally. And we were talking about this incredibly cold nanokelvin temperature. And when they come together sufficiently close, they must start to form a solid and crystallize. And then you lose this Bose-Einstein condensate. And that's indeed what experiments show. So once you actually cool the system down in donut shape, you can observe that Bose-Einstein condensate indeed forms. And depending on how you do it, you see different levels of flow. But that is always quantized in a unit of integers. So pass that around, pass that around. And if you look at how much is flowing as a function of time, if you don't have Bose-Einstein condensate, because of friction, it starts to decay exponentially. That's what you would normally expect. But what you see is the plateau. Stay with a fixed flow for a long period of time before it starts to do this crystallization and you lose the Bose-Einstein condensate in the end. And while it's actually on the plateau, it just keeps flowing. That's why it's a persistent flow, which means that there is zero viscosity. And I'm talking about this dilute gas of cold atoms here because that's theoretically easier to deal with weak interaction. But the real persistent flow you can get is something that doesn't crystallizes, so that it gets lost. And liquid helium is precisely that. At the atmospheric temperature, there's no solid phase. It stays liquid all the way down to 0 Kelvin. So persistent flow is really persistent flow. And I have read about an experiment where they let it actually flow like this for something like a year. So zero viscosity, it's really persistent. And that's because integer cannot become a real number. Integer has to be integer. And this kind of thing is called pathological protection. And you might have heard about this topology being a somewhat hot subject in condensed matter physics, also in other areas of physics too, because the topology is the reason why this has to be integer. Simply that is a periodic boundary condition, and something is quantized as a solution to classical field equation. Even though it's a classical solution, there is a quantization of flux, and integer cannot continuously change. It can only jump, therefore there's a good protection to the system, and that appears as a persistent flow of the superfluid. So that's the first example you see that topology is something actually very interesting and exciting in many areas of physics. Okay, let me stop here, and I post a new homework problem, and see you next week. And also there's an office hour later today. I have to move it from 3 to 5. But I hope you can make 5 o'clock if you have any questions.